Welcome back to the course on computer graphics. In this video, we are going to see the remaining part of module 6. First, we will see gray level histogram. In statistics, we have already studied. Studied histogram. Histogram. What is histogram? Histogram is a graphical representation showing a visual impression of the distribution of data. That is. Here is an example of a histogram. Here you have some events 0, 1, 2, 3, and the frequency of occurrence of each event is shown here graphically. Okay, so the x-axis here shows the event and the y-axis shows the frequency of this occurrence of each event. Okay, so this is a graphical representation showing a visual impression of the distribution of data. Okay, so in image histogram, that which we are going to see here. Okay, in an image histogram, it's similar to a histogram, or it is a type of histogram that acts as a graphical representation of the lightness or color distribution in a digital image. That is, here we are going to represent an image graphically, which show in graphically, and the data which is represented graphically is the color distribution or the intensity of light on an image. Okay, so what you are going to do is it plots the number of pixels for each gray level in an image. Okay, so the x-axis will be in an image histogram, the x-axis will be the gray levels, and the y-axis will be the number of pixels for each value, or the it is going to graphically represent the color distribution in a digital image. Okay, so histogram of images provide a global description of their appearance, and the histogram of an image represents relative frequency of occurrence of various gray levels. Okay, so this histogram can be plotted in two ways. One way is as actually what I have already told, that is, the x-axis will be the gray levels and y-axis will be the number of pixels in each gray level. Okay, so here this shows an example. This image is an example of a histogram plotted in this way. Okay, so here you have x-axis is different gray levels. Here there is 0, 1, 2, 3, 4, 5, 6. Okay, so the histogram is showing gray levels in the range 0 to 6, and here in the y-axis is nk, which represents the number of pixels. So for 0 gray level, there are 40 pixels, so that is plotted here. So 1 gray level 1, there are 20 pixels, that is plotted here. For gray level 2, there are 10 pixels, which is plotted here. So similarly for 0 to 6, all the gray levels, for all the gray levels, the number of pixels, corresponding number of pixels are plotted here. So this is a histogram. This is a histogram. This is one method for plotting a histogram. Okay, the histogram of a digital image with gray level in the range 0 to L minus 1 is a discrete function h of rk equal to nk, where rk is the kth gray level and nk is the number of pixels in the image having gray level rk. Okay, so this can be this is also represented as a discrete function h of rk, where h of rk means rk is the kth gray level. So if it is h of 0, h of 0 will be the number of pixels corresponding to that gray level. So h of 0 will be 40, h of 1 will be 20, h of 2 will be 10, like that. Okay, so it can be represented as a discrete function h of rk, where rk is the kth gray level and nk is the number of pixels in the image having gray level rk. Okay, so that is the first method for plotting a histogram for a image. Then second method is uh, after normalizing the values. Okay, so it's a very common practice to normalize a histogram. We normalize this histogram because all the values will be between 0 and 1. So the maximum will be always, the maximum value plotted will be always 1. Okay, so then you can know that the maximum value 1 will be gray level with color white, and 0 will be black. Okay, so the 0 to 1, 0 will be black will be 0 and white will be 1. So you are going to plot it between 0 and 1 in case of the second method. Okay, so here we are normalizing a histogram. So here the x-axis again is the gray level itself, but the y-axis will be the probability of occurrence of gray level. Okay, so in this histogram, this x-axis will be same as that of the first method, that is the gray levels, but here instead of number of pixels we are going to plot the probability of occurrence of each gray level. Okay, and this probability is given by p of mu k, that is equal to nk by n, where mu k is the gray level, nk is the number of pixels and in the kth gray level, and n is the total number of pixels in an image. Okay, so probability of a particular gray level is calculated using this equation, that is number of pixels in that gray level by total number of pixels in an image. Okay, so that is the probability, and this probability is plotted on the histogram. Okay, the sum of all components of a normalized histogram will be equal to 1. Okay, so that is a normalized histogram. Okay, so you have two methods. In first method, x-axis will be gray level and y-axis is number of pixels, and in second method, x-axis will be gray level itself, but the y-axis will be the probability of occurrence of gray levels. Okay, and different images can have a same histogram. For example, if you see these images, you can see in the first image half of the pixels in this image will be is white and other half is gray. Similarly, in this figure also, if you see one part, about half of the pixels is gray and other half is white, and on this image also same. So when you draw a histogram for all these three images, they are going to be having same histogram only. Okay, so half of the pixels are gray and half are white for all the three. So the same histogram because they have the same statistics. Okay, so this means that if you have a histogram, you cannot reconstruct a image from that histogram. Okay, you can have different patterns for the data available in the histogram. Okay, you have only different pixels and the number of pixels with a particular intensity or particular gray level value. Okay, so from that many patterns can be drawn. So you cannot reconstruct an image from the histogram. Okay. Then why these histograms are used? Histograms are the basis for numerous spatial domain processing techniques, and histogram manipulation can be used effectively for image enhancement. Then another use is that histograms can be used to provide useful image statistics, and the information derived from histograms are quite useful in other image processing applications such as image compression and image segmentation. These are all the reasons why you use histograms. Okay. Then now we are going to see different types of histogram. Okay, so here these are the images which shows different types of histogram. The first one is a dark image histogram. Then you have bright image histogram, low contrast image histogram, and equalized image histogram, equalized or high contrast image histograms. Okay, so a dark image histogram means here uh, the uh, the graph is concentrated to the lower side or lower in gray level values. See, it is concentrated to the left of the uh, graph. So that is dark image histogram. In dark image histogram, the components of the histogram are concentrated on the low side or dark side of the grayscale. Okay, and if you see bright image histogram, this is just opposite of dark image. That is, here this graph will be more concentrated to the bright side or the high side of the graph. Okay, see here it is concentrated to the right side of the that is bright image histogram. That is, here the gray levels will be of higher values. Okay, and in low contrast image histograms, it's a very it will be a narrow graph which is mostly concentrated to the middle of the graph. Okay, so here it is mostly concentrated to the middle of the graph. Okay, that is low contrast image. And in equalized image, it will be broadly distributed. Okay, so this components this equalized image is also called high contrast image, and it covers a broad range of grayscale, and that the distribution of pixels is not too far from uniform, with very few vertical lines being much higher than the others. So, it is reasonable to conclude that an image whose pixels tend to occupy the entire range of possible gray levels, and in addition tend to be distributed uniformly, will have an appearance of high contrast and will exhibit a large variety of gray tones. So, the last graph represents the best image. Okay, so here this equalized image is going to represent the best kind of image. Okay, so the last graph represents the best image, and it is a high contrast image, and our aim always would be to transform the first three histograms into the fourth type, and that means all these three types are concentrated to some area, right? So our aim will be to broaden that, or you have to increase the dynamic range of the image. Okay, so for all these three, dark image, bright image, and low contrast image, um, you have to convert this to an equalized image or a high contrast image, that is histogram processing. Okay, so what we are going to do is simply increase the dynamic range of the image. Okay, So that is histogram processing, and in histogram processing there are two methods for enhancing the contrast. First one is histogram stretching, and second is histogram equalization. Okay, so histogram stretching. In histogram stretching, the in this process, it increases the dynamic range of the image and hence improves the contrast of the image. Okay, so in this process, the basic shape of the histogram is not modified, but the entire range of the image of histogram values is stretched. Okay, so basic shape of the histogram will remain the same, but the entire range will be, we are going to stretch the entire range. Okay, we'll see how it is done. Okay, so before stretching process, it is necessary to specify the upper and lower limits of the limits for pixel of normalized range. So the limit values depends on the type of image. For example, if 8-bit image, limit values ranges between 0 and 255. Like that. Okay, so the limit value will depend on the type of image, whether it is 8-bit or 16-bit image, like that. So if it is an 8-bit image, the range will be from 0 to 255. So in that, again you have to find the, in that image, which is the upper limit and which is the lower limit of pixels of the normalized range. Okay, and then what you do is you perform a simple function, that is S is equal to T of R equal to S max minus S min by R max minus R min whole into R minus R min plus S min. So this is going to give the values for the new histogram, or let's stretched histogram. Okay, so here S max is the maximum limit value of the image and S min is the minimum limit value of the image. R max is the highest pixel value of the image and R min is the lowest pixel value of the image. So when we can do an we can do a problem so that you understand it better. Okay. So here you have to perform histogram stretching so that the new image has a dynamic range of 0 to 7. Okay, so this is the given values for the histogram, that is 0, 1, 2, 3, 4, 5, 6, 7 is the range of values, and the number of pixels in each gray level is given here. So it is what you want to do is a histogram stretching. Okay, so using this data, you can draw a histogram which will look like this blue one. Okay, so this is the original histogram. What you have to do is you have to stretch this histogram so that it give a more high contrast image. Okay, so for this you have to use this equation, S is equal to T of R, which is this function, that is equal to S max minus S min R max by R max minus R min into R minus R min plus S min. So here you have to find the values for S max, S min, R max, R min, R, etc. Okay, so what is S max? S max is the maximum limit value of the image and S min is the minimum limit value of the image. Okay, so that means maximum limit value, you have already said it have to be stretched to the range of 0 to 7. So the minimum limit value of the image will be 0 and maximum will be 7. So S min is 0 and S max is 7. Okay, so the gray level value, the maximum value can be 7 and minimum value can be 0. Okay, we have already told it should be stretched within this range. Okay, So 0 and 7 is Smin and Smax. Then Rmin and Rmax. Rmin is the maximum, Rmin is the minimum pixel value or the lowest pixel value in that image, or for this image which is the minimum pixel value. That means here 2, this gray level 2 has the minimum pixel value, and it is a maximum or the highest pixel minimum, it's not minimum, it's the lowest pixel value of the image. Okay, so the lowest pixel value for others, for 0 and 1, the pixel number of pixels is 0. So the lowest pixel value is 2. From 2 only the number of pixels are shown. So that means 0 and 1 is not, gray levels are not there in that image. So in this image 2 is the lowest pixel value, and 6 is the highest pixel value, because 7 also again number of pixels is 0. So Rmin is 2 and Rmax is 6. Okay, so from this so you got Rmin, Rmax, Smin and Smax. So you can use this equation. Okay, so first one is Smax minus Smin by Rmax minus Rmin, that is slope. So you can first find the slope, that is Xmax minus Smin by Rmax minus Rmin, that is 7 minus 0 by 6 minus 2. You get 7 by 4 or 1, that's equal to 1.75, and then you apply this equation, that is the slope into R minus Rmin. So 7 by 4 into R minus Rmin is 2, R minus Rmin plus Smin. Okay, so you get S equal to 7 by 4 into R minus 2, because S is equal to, S min is equal to 0. Okay, then for each R value you are going to apply this equation. Okay, so here minimum R value is 2. From 2 to maximum R value 6, you are going to find the corresponding S value. So for 2 you find S is equal to 0. For 3 you apply 7 by 4 into 3 minus 2. So you get 2, 1.75, which is rounded to 2. Then for 4 it will be 7 by 4 into R minus 4. 4 minus 2, that is equal to 3.5. You get the value 4. So for R equal to 5, S equal to 5. For R equal to 6, S is equal to 7. So this is the S values for corresponding R values. Okay, now using this you have to make a table for gray levels 0 to 7 using this. Okay, so for gray level 0, okay, here for gray level 0, here for gray level 0 represents R is equal to 2. Okay, so for 2 number of pixels is 50. Okay, so so this S equal to 0 will have number of pixels equal to 50. Okay, so 0 will have number of pixels equal to 50. Then for 1, gray level 1, here there is no value 1, so number of pixels will be 0. Then gray level 2, here gray level 2 corresponds to R equal to 3. Okay, so for 3 number of pixels is 60. So here for gray level 2 the number of pixels will be 60. Okay, then you look for gray level 3, there is no 3 in this S, so the number of pixels will be equal to 0. then take 4 here. For s equal to 4 corresponds to r equal to 4. So for gray level 4, the number of pixels is 50. So same here, for 4 the number of pixels is equal to 50. Then next is 5. This 5 here corresponds to 5 in the 5 in the original image. So corresponding number of pixels is 20. So 5, 20 here. Then 6, there is no 6 here, so the number of pixels is 0. Then 7, so here 7 is equal to 7 corresponds to r equal to 6. So corresponding for r equal to 6, the number of pixels is 10. So here 10. Okay, so using this data you draw a histogram and you get this histogram, a graph like this, and which is a stretched histogram. See, here the values are concentrated between 2 and 6, and here it is stretched so that the range is increased to 0 to 7. With earlier it was only between 2 and 6, here it is stretched to 0 and 7. Okay, so this is going to give a more high contrast image. Okay, this is how you do histogram stretching. Okay, then the second type of or second method for performing histogram processing is histogram equalization. Okay, equalization is a process that attempts to spread out the gray levels in an image so that they are evenly distributed across their range. Okay, so it reassigns the brightness values of pixels based on image histogram. Okay, the histogram of resultant image is made as flat as possible and provides more visually pleasing results across a wide range of images. The different steps to perform histogram equalization is: first, find the running sum of histogram values. Then normalize the values from step 1 by dividing with the total number of pixels. Then multiply the values from step 2 by the maximum gray level value and round it. Then finally map the gray level values to the results from step 3 using a 1-to-1 correspondence. Okay, so that's given here. Okay, so this is an example. Here you have to perform histogram equalization of this image. Okay, so this matrix represents an image. So what you're going to do is you are going to perform histogram equalization, that is you are going to spread out the gray levels in an image so that they are evenly distributed across their range. Okay. Okay, so here the maximum value found to be is 5 in this image. The maximum gray level value found is 5, and the minimum we need a minimum of 3 bits to represent this 5. So there are 8 possible gray levels, that is from 0 to 7. The histogram of the input image, this image is shown here, that is you have gray level 0 to 7. The number of pixels, corresponding number of pixels is given. For 0, no number of pixels is 0. For gray level 1 it is 0. For gray level 2 it's 0. For gray level 3 there are 3 pixels. There are 6 pixels, that is 1, 2, 3, 4, 5, 6 pixels are available. For gray level 4, 14 pixels are available. there is 14 pixels in this image. Then for gray level 5 there is 5 pixels, and for 6 is 0 and 7 is 0. Okay, this is the histogram for the input image. So to perform histogram equalization, you have to perform these steps here. So first you have to find the running sum of the histogram values. Okay, so running sum is also known as cumulative frequency distribution, which you must have already uh, studied in statistics. That is, you have to find the cumulative values. Okay, so this is the histogram data for the original image. So what you have to do is you have to find the cumulative value. Okay, so for gray level 0 the number of pixels is 0. Then for gray level 1 the cumulative frequency distribution will be earlier plus this value. So again it is 0 and 0, so 0 itself. For 2 you have to add the earlier value plus the number of pixels in this gray level, that is again 0. Then for gray level 3 you have to add uh, the number of pixels 6 to this value, that is 6 itself. Then for gray level 4 the CFD will be 6 plus 14, that is 20. Then for gray level 5 it will be 20 plus 5, that is 25. Then for gray level 6 it will be 25 plus 0, that is 25 itself. And for gray level 7 it will be 25 plus 0, that will be 25 itself. Okay, so you have to find the cumulative frequency distribution, that is running sum of histogram values. Okay, then step 2, you have to divide the running sum obtained in the last step by total number of pixels in pixels. Okay, so here the total number of pixels is 25. Okay, so if you see this image, the total number of pixels is 25. Okay, so what you have to do is for each cumulative frequency value should be divided by 25. So 0 by 25, 0 by 25, 0 by 25, 6 by 25, 20 by 25, 25 by 25, 25 by 25 and 25 by 25. Okay. Then step 3, you have to multiply the values that you got in step 2 by the maximum gray level value. Okay, so here the maximum gray level value should be 7 in this example. Okay, so the result of this value will be rounded to the closest integer. Okay, so the earlier values were this. CFD by total number of pixels is here. This you have to multiply by the maximum gray level value, which is 7. So 0 by 25 into 7, that is rounded to the nearest integer value, which is equal to 0. 0 by 25 into 7, 0. 0 by 25 into 7, 0. 6 by 25 into 7, which will be rounded to 2. 20 by 25 into 7, which will be rounded to 6. 25 by 25 into 7, which is equal to 7. 25 by 25 into 7, that is equal to 7, and 25 by 25 into 7 is equal to 7. Okay, so this is the result of step 3. Okay, so this will give the result of step 3. And finally you have to map these values to the results from for the gray level, map the gray level values to the result from step 3 using a one-to-one correspondence. Okay, so you get for gray level 0, so you get this one. So for gray level 0, 0, 1, 0, 2, 0, 3, 2, 4, 6, 5, 7, 6, 7, 7, 7. So this is the original gray levels or the gray levels in the original image, and these are the histogram equalized gray levels. Okay, so what you are going to do is you are going to replace the gray level values in the original image with this values. Okay, so in this case, this is the original image. Here in this image, these values will be replaced by the new values. Okay, so here all these fours will be replaced by 6. Okay, for 4 corresponding equalized level is 6. Okay, so all the 4s will be replaced by 6. All the 3s will be replaced by 2. Okay, so see here all the 3s are replaced by 2, and all the 5s, 6 and 7s. Okay, here the maximum value comes here is 5 only, so all the 5s will be replaced by 7. See, all the 5s are replaced by 7. So uh, this is the final equalized histogram image. Okay, so that is histogram equalization. Okay, so these are the two methods for histogram processing. Okay, so next topic is edge detection. Okay, edge detection, uh, in an image you can find the edges of the image. Okay, the sudden changes or discontinuities in an image are called edges. Okay, so you can see this example. This is the original image. So for the same picture, you have identified or detected the edges here. Okay, see, this is the edges. Okay, so this this is basically sudden changes or discontinuities in an image. Okay, significant transitions in image are also called as edges, and edges are significant local changes of intensities in an image. Okay, basically to detect the edges you have to see sudden changes or discontinuities in images, or any changes in the intensity values. Okay, so that can be in that way you can detect the edges. So this is the original image, and this is the edges of that image. Okay, so an image processing technique for finding the boundaries of objects within images is called edge detection, and it works by detecting the discontinuities in brightness, and it is used for image segmentation and data extraction in areas like image processing, computer vision, etc. Okay, so basically you have to detect the discontinuities in brightness or intensities. Okay, so generally edges are of three types, that is horizontal edges, vertical edges and diagonal edges. And basically there are different methods to find edges. Uh, they are Privet operator, Sobel operator, Robinson compass mass, Krish compass mass, Laplacian operator and Roberts operator, and all these finds all these mass find edges. Some find horizontal edges, or some find horizontal and vertical edges, and some find in one direction only, and some find in all directions. Okay, basically these are the different methods of edge detection, and we are going to see only three of this, that is Privet operator, Sobel operator and Roberts operator in detail. We'll just see what are all these operators or mass. Okay, so Previtt operator is used for detecting edges horizontally and vertically also. Sobel operators are also similar to Previtt operator, and it is also a derivative. It is also a derivative mass which calculates the edges in both horizontal and vertical direction with some difference from it's almost very similar to Prewitt operator. We'll see this in detail. Okay, then Robinson compass mass is also known as direction mass. In this operator we take one mass and rotate in all 8 compass major directions to calculate the edges of each direction. Okay, then Kirsch compass mass is also a derivative mass which is used for finding edges in all the directions. And Laplacian operator is again another derivative operator which is used to find edges in an image. Um, Here it is a second order derivative mass, and it can be further divided into positive Laplacian and negative Laplacian. We are not going to see much detail about it. And finally, Roberts operator. This method is based on difference between adjacent pixels. Here +1 and -1 are explicitly used to find the edges. The difference is called as forward differences, which also we will see in detail. Okay, so first one is Prewitt operator. So this operator detects two types of edges, that is horizontal edges and vertical edges. Edges are calculated using difference between corresponding pixel intensities of an image. Okay, so changes in an image can only be calculated using differentiation. So that's why these operators are also called derivative operators or derivative mass. Okay, so basically to detect the horizontal edges and vertical edges, you have to calculate the difference between the corresponding intensities, pixel intensities of an image, and this can be calculated only using differentiation method. So that is why it is called a derivative mask or a derivative operator. Okay, so all this derivative mass should have the following properties, that is opposite sign should be present in the mass, sum of the mass should be equal to 0, and more weight means more edge detection. Okay, so these should be the properties of all these derivative mass. Okay, and the Prewitt operator provides two mass, one for detecting the horizontal direction and the other for detecting the vertical direction edges. Okay, so we are going to see the mask for horizontal direction and also for vertical direction. So it provides two mass, Prewitt operator. So first one is vertical direction. So this is the mask, this one -101 -101 -101. This is the vertical uh, uh, or the mass for detecting the vertical edges. Okay, or the edges in the vertical direction. So when you convolve this mass on an image, it will give you a vertical edge of an image, and when we apply this mass on the image, it actually prominence the vertical edges. Okay, and it simply works with like a first order derivative and calculate the difference of pixel intensity in an edge region, and as the center column is of 0, it does not include the original values of an image, but rather it calculates the difference of right and left pixel values around that edge. Okay, so that's how it works. Since um, these values are given as 0, right? So what happens is it does not include the original values of the image, but it calculates the left difference between the right and left pixel values around this edge. Okay, so that's how it detects the vertical edges, and this increase the edge intensity, and it become enhanced comparatively to the original image. And above mask will find the edges in vertical direction, and it's because the zeros column is in the vertical direction. Okay, so this is in the vertical direction, that's why it finds the vertical edges. Okay, similarly, Privet operator also provides a horizontal mask. See, the horizontal, in the horizontal mask, this zeros are in the horizontal direction. That's why it detects the horizontal edges. Okay, so this mask will find edges in horizontal direction, and it is because the zeros column is in horizontal direction. Okay, so when you convolve this mass onto an image, it would prominent the horizontal edges in the image. As the center of the mask is of 0, so it does not include the original value, and finds the difference between the above and below pixel intensities of the particular edge. And that's how it finds the horizontal edges. Okay, thus increasing sudden changes of intensities and making the edge more visible. Okay, and in a picture, when we apply the vertical mask, all the vertical edges are more visible than original image. And similarly, when you apply a horizontal mask on image, so all the horizontal edges will be more visible. I think I have a, yeah, so this is a example image. Okay, so this is the original image. This is after applying vertical mask on this image, all the vertical edges, see, all the vertical edges are visible here. And after applying horizontal mask on this image, you can see, all the vertical, I mean horizontal edges more clearly. Okay, so in this way we can detect both horizontal and vertical edges from an image. Okay, that was Privet operator. Then you have Sobel operator. Sobel operator is similar to Privet operator, that is it detects two types of edges, that is horizontal edges and vertical edges. And here edges are calculated by using differences between corresponding pixel intensities of an image. But the major difference is that in Sobel operator, the coefficients of mass are not fixed, and they can be adjusted according to our requirement, unless they do not violate any property of derivative mass. Okay, so here the coefficient of the mass is not fixed. Okay, and it again provides two masks, one for detecting the edges in horizontal direction and another for detecting edges in the vertical direction. Okay, so this is a mask, Sobel operator mask for detecting the vertical edges. Okay, and this actually works similar to the Privet operator mask. The only difference is that it has 2 and -2 values in the center of first and third column. Okay, see here, it was in Privet operator mask, it was all -1s in the left side, left on in the first column, and all ones in the third column. So here these values are changed to -2 and 2. Okay, that is the only difference in the mask. When applied on an image, this mask will highlight the vertical edges. Okay, so because the zeros are in the center column, So it is in vertical direction, it is going to detect the vertical edges, and it simply works like the first order derivative and calculate the difference of pixel intensities in a edge region. And as the center column is of 0, it does not include original values of an image, but it calculates the difference of right and left pixel values around that edge. And also the center values of both the first and third column is 2 and -2 respectively, and this give more more weightage to the pixel values around the edge region, and this increase the edge intensity and it become enhanced comparatively to the original image. Okay, so since we are giving more weight, it is going to give more enhanced edges. Okay, then this is a horizontal mask, or the mask, Sobel operator mask, to detect the horizontal edges. Here the zeros is in the horizontal direction, so it is going to detect the horizontal edges. When you convolve this mask onto an image, it would prominent the horizontal edges in an image, and only difference is that these values here in Sobel, in Pruitt operator, it was all -1 in the first row and all ones in the third row. Here these values in the middle of this two rows are changed to 2 and -2. uh, so as the center row of the mask consists of 0, so it does not include the original values of the edges in the image, but it calculates the difference of the above and below pixel intensities of the particular edge, and it thus increases the sudden change of intensities and make the edges more visible. Also, if you compare the result of Sobel operator with Pruitt operator, you will find that Sobel operator finds more edges or make edges more visible as compared to Pruitt operator. This is because the Sobel operator, we have allotted more weight to the pixel intensities around the edges. Now we can also see that if we apply more weight to the mask, the more edges it will get for us. Okay, so here, since we have given more weight, it is going to detect more edges compared to Pruitt operator mask. Okay, and there is no fixed coefficient in Sobel operator, so here it's another weighted operator. So here, instead of -2 2, it is changed to -5 5, and these values are not fixed values, you can change it. Okay, so if you give more weight, it will detect more edges. So this is going to give more edges as compared to the previous maps, because we have more vertical edges compared to the previous maps, because we have allotted more weight in the mask. Finally, you have Roberts-Krauss operator. A Roberts-Krauss operator performs a simple quick to compute edges on an image. As it's again a differentiation operator. The idea behind Roberts-Krauss operator is to approximate the gradient of an image through discrete differentiation, which is achieved by computing the sum of squares of differences between diagonally adjacent pixels. Okay, so here you are going to find the sum of squares of differences between diagonally adjacent pixels. Okay, so here, according to Robert, the edge detector should have the following properties. That is, it should produce the produced edges should be well defined. The background should contribute very little noise as possible, and the intensities of edges should correspond as close as possible to what a human would. Okay, this should be the properties for a edge detector according to Roberts. Okay, and with this criteria he has proposed an equation that is basically they are going to compute the sum of squares of differences between diagonally adjacent pixels. Okay, so that is given here. So okay, here you have find root of uh, sum of squares of difference between diagonally adjacent pixels. Okay, so here yij and yi plus 1 j plus 1, they are diagonally adjacent pixels, and they have found the different squares of difference between these pixels. Again, yi plus 1 j and yi j plus 1 is another diagonally adjacent between. They have found a difference between these two pixels and the square of this, and so zij is the computed derivative, which is the root of this yij minus yi plus 1 j plus 1 the whole square plus yi plus 1 j yij plus 1 the whole square. Okay, and yij will be equal to root of xij, where x is the initial intensity value in the image. Okay, so using this you the result of this operation will highlight the change in intensity in diagonal direction. Okay, so in order to perform edge detection with this Roberts operator, what you do is you convolve the original image with these two convolution masks. One is mx and my. Mx is 1 0 0 minus 1 and my is 0 1 1 minus 1 0. When you if you see this, you can understand that mx my is a mass which is obtained by simply rotating this mx in 90 degrees. See, so just it minus 1 0 1 0. Okay, see, this is how you get my. Okay, so this the Roberts Krauss operator uses diagonal directions to calculate the gradient vector. Here zeros are in the diagonal direction. See, in one mass it is in this diagonal direction, and the other mass it is in this direction. So the Krauss operator uses the diagonal direction to calculate the gradient vector. Okay, so let xy be a point in the original image and xy be the point in an image formed by convolving with the first kernel, and xy be a point in an image formed by convolving with the second kernel. Then the gradient can then be defined as gxy equal to root of g square xy plus g square gy square gx square plus gy square, sorry. Okay, so that is the gradient, and direction of gradient can be defined as arctan of gy xy plus gx xy minus 3 pi by 4. Okay, that is all about Roberts Krauss operator.